Hello and welcome to Neuron short number 2 about the basic architecture of a processing board and the structure of the interfaces in Cerebrum. In the first video I explained that we designed a generic processing board with the equivalent power of 16 Synapse modules on a single card, and how the software on this board defines the board's capabilities and functionality. To be able to achieve this flexibility, the processing board has to have a certain basic architecture to which all software variants can map their functionality. Here you have a Neuron processing board. What immediately stands out is this big heatsink under which there's a very powerful FPGA. For those who are not familiar with that term, an FPGA, or Field Programmable Gate Array, is a processor which can be programmed to only perform very specific tasks and instructions. Compared to a generic processor, or CPU, which you can also find in your PC or laptop for instance, an FPGA has much lower latency, higher bandwidth I/O and is much more power efficient. Each specific task and each input or output uses a certain number of logic blocks of the FPGA. And although the FPGA on a Neuron board is one of the biggest ones currently available, it of course does not have an infinite amount of logic blocks. The more functionality you add in the software, the less channels you can support. The more inputs and outputs you add, the less processing functionality you can support. All software variants follow the same structure. To explain this structure, I'm going to draw a block schematic you might be familiar with from Synapse next to a connector panel of a Neuron board. First, there's the IP I/O. Our QSFP interfaces, of which there are two for redundancy, are truly single MAC 100 gigabits per second. In the software, a certain amount of IP audio and video input and output streams is defined. On top of these IP I/O, you can have SDI input and outputs when the SDI expansion board is installed. This optional board adds 8 UHD capable inputs, 8 UHD capable outputs and 24 full HD capable bidirectional SDI connections. The bidirectional SDI can individually and on the fly be configured as an input or as an output. All the inputs are fed into a big multiplexer, or MUX in short. Behind this MUX are a maximum of 32 full HD processing paths, divided in groups of 4. Which processing is possible in these groups, so whether you can for instance upconvert HD to UHD, or whether you can do color correction or HDR conversion or audio embedding, etc., is again dependent on the software. Whenever UHD is enabled, 4 HD paths merge into one UHD path. Thanks to the big MUX in front of the processing paths, you can select any of the SDI or IP inputs to be the source of each individual processing path. This is a big advantage over some competitors, where the link between the inputs and the processing paths is hardwired. On top of that, thanks to the MUX behind the processing paths, you can freely assign each processed signal to any of the IP or SDI outputs. You can even assign one processed signal to multiple outputs. Also part of the generic structure is the audio matrix, to allow audio channel swapping and processing between various ST2110 audio streams and the de-embedded audio channels. The reference and PTP circuits for timing and frame synchronization, the microcontroller for configuration and control, and the extra expansion slots to add SSD storage, an Arduino Dante board and a CPU or GPU system on a chip. Each software variant features a different combination, so a different trade-off of functionality versus I/O, using the maximum number of available logic blocks in the FPGA. So each version features a different mix of SDI I/O availability, number of IP input streams, number of IP output streams, the number of processing paths, processing capabilities per processing path, and the redundancy standards. More about that in the following Neuron shorts. And remember, all firmware variations run on the same hardware. If you want to, for instance, change your current processing board from only doing SDI to IP bridging into a board that can also do up, down and cross conversion, you can reprogram your board without having to add or exchange any hardware. This generic structure of the processing board is reflected in the graphical user interfaces of Neuron in Cerebrum. We developed a more visual control interface, which makes it easier and more intuitive to configure the boards than the usual list of parameters you so often see with competing products. Next to the hardware status tab, in which you can monitor things like temperatures, fan speeds and SFP statuses, there is the video paths tab, which looks a bit like the block schematic we just drew. This interface, which visualizes the video workflows of your Neuron board, looks very similar for all variants, only showing different numbers of inputs, outputs and processing paths, and showing other processing abilities per path. On the left side you see the SDI inputs, of which you can set SDI 9 to 32 to be either an input or an output by clicking on it and changing this setting to input or output. Right next to that are the IP video input streams. Again, the number of IP video input streams varies per software version. You can click on each button to change the IP settings of each input stream. Then you see the big mux to visualize that there is no direct link between the inputs and processing paths, which are shown behind the mux. The processing paths are grouped by 4 and labeled A1, A2, A3, A4 and then B1, 2, 3, 4, etc. all the way to H4 in this case. You can select any of the SDI and IP inputs to be your main and your backup source of each path. If the card is set to backup fail, the individual paths will switch to the selected backup input if the selected main input is lost, which is also quite unique. Configuring this in the right way, you can even create a fallback scenario from IP to SDI in case your IP infrastructure fails entirely. You can see the status of the selected input by the green or grey colored dot next to the selection box. Then you see the actual processing paths, with red, blue or grey arrows, indicating if this path is currently using the main or the backup input or if there's no video at all. In between the arrows are the various processing blocks that are available on this board, in which you can configure, in this case, the frame sync, color corrector, the audio embedder and the audio processing. Then we see the output format setting, mainly for timing in this case, but it can also be used for format conversion when using a convert. More about that in one of the following Neuron shorts. On the right hand side you see the outputs. Here you can select which processed channel, A1, A2, A3, etc. is assigned to which individual SDI and IP output. Again, there's no direct relation between, for instance, path A1 and output 1. You can freely select which path goes out where. Let's quickly go over the other tab. The SDI I/O tab provides an easier, more straightforward way to configure the SDI inputs and outputs. In the IP Video I/O and IP Audio I/O tabs, you see an overview of all the IP input and output stream settings, like IP address, port number, media type, etc. I'll explain these in detail in the following videos. Here is the Audio Paths tab, showing where the audio matrix channels are coming from and how they are processed. This is the Network Setting tab. The General Settings tab, where you can find all kinds of board-wide settings, like Genlock and PTP settings. And finally the IP Metrics tab, for monitoring your IP input stream statistics. The Monitoring and Object Browser tabs are default Cerebrum tabs to show the event log of this board and a list of all the controllable parameters. This concludes our high-level overview of the processing board's hardware architecture and the generic structure of the Neuron interface, which all software variants have in common. In the next Neuron short, I'll give a more detailed overview of the abilities of the available bridge software variants. See you then!